Hello everyone, today we are going to start with a new topic of understanding complexity analysis. We will also analyze algorithm efficiency using big O notation. So let's get started. What exactly is complexity analysis? It's essentially a method to evaluate how efficiently an algorithm performs as the size of the input grows. Complexity analysis measures both time complexity, which refers to speed, and space complexity, which is about memory usage. Ultimately, it helps us compare different algorithms in an objective way, allowing us to choose the best one for a particular task. Why is complexity analysis so important? Firstly, it enables performance prediction. We can estimate how runtime and memory usage will scale as we deal with larger inputs. Secondly, it allows for objective algorithm comparison, helping us determine which solution is more efficient. Thirdly, it helps us to focus optimization efforts in our code, pinpointing the areas that will yield the greatest performance improvements. Finally, complexity analysis aids in scalability planning, ensuring that our systems can handle future growth and larger workloads. Let's dive into big O notation. Big O notation describes the upper bound of an algorithm's growth rate. It represents the worst-case scenario for algorithm performance. Big O notation is written as O of f of n, where f of n represents the growth rate. Big O notation focuses on dominant terms as input size approaches infinity. Here are some common time complexity classes. First, O of 1, which is constant time. An example of this is array access or simple calculations. Next is O of log n, which is logarithmic time. Binary search and balanced tree operations fall into this category. Then we have O of n, or linear time, which is exemplified by simple loops in linear search. O of n log n, or linearithmic time, is seen in efficient sorting algorithms like merge sort. Lastly, O of n squared, or quadratic time, is common in nested loops and bubble sort. Let's start with O of 1, constant time complexity. In constant time complexity, the operation time remains constant regardless of the input size. Examples of constant time operations include array index access, hash table lookups, stack push or pop operations, and basic arithmetic operations. In the provided code, the function get_first_element has a time complexity of O of 1, because it always takes the same amount of time to retrieve the first element of an array, regardless of the array's size. Similarly, adding an element to a stack using the push function also has a time complexity of O of 1. Next, let's discuss O of n linear time complexity. In linear time complexity, the operation time grows linearly with the input size. Examples of linear time operations include iterating through arrays or lists, linear search algorithms, simple for loops, and computing the sum or average of elements in a list. In the provided code, the linear_search function has a time complexity of O of n, because it iterates through each element of the array, once to find the target value. Similarly, the calculate_sum function also has a time complexity of O of n, because it iterates through each number in the list to compute the total sum. Now let's explore O of n squared quadratic time complexity. In quadratic time complexity, the operation time grows with the square of the input size. Common examples include nested loops, bubble sort, selection sort, comparing all pairs of elements in a list, and simple two-dimensional grid operations. In the provided code, the bubble_sort function has a time complexity of O of n squared because it uses nested loops to compare and swap elements in the array, resulting in a quadratic growth rate as the size of the array increases. Lastly, let's discuss O of log n, logarithmic time complexity. In logarithmic time complexity, the operation time grows logarithmically with the input size. This typically involves algorithms where the input size is halved in each step. Examples of logarithmic time operations include binary search algorithms, operations on balanced search trees, and divide and conquer algorithms. In the provided code, the binary_search function has a time complexity of O of log n, because it repeatedly divides the search interval in half until the target value is found, or the interval is empty. This logarithmic behavior makes binary search very efficient for searching sorted arrays. Now let's compare the efficiencies of different algorithms. In this table, we compare the performance of various algorithms as the input size increases. You can see how the runtime increases for each complexity class as n grows. Keep in mind that as input size grows, the efficiency differences become dramatically more significant. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.